The next algorithm that we have to discuss is for modular multiplication. And before we start discussing the algorithm for modular multiplication, we need to collect some more basics from number theory. I hope you remember about the basics that we reviewed from number theory, including the division theorem, factors, and GCD. Today we are going to discuss about prime numbers, pair of numbers which are relatively prime, and also about modular number systems. So we need to collect some more information from number theory. First we can see what are prime numbers. A number P is called prime if it has only trivial factors. We know that for any integer the trivial factors are 1 and that integer. A number is called prime if that number is having only one as the factor other than that number itself. We can look at examples. We can see that 2 is a prime. It is the only even number which is prime. It satisfies the definition because if you look at the factors, only 1 and 2 are the factors. Another example is 3, only 1 and 3 are the factors. 11 is also prime because only 1 and 11 are the factors of 11. 13 is also prime because here as well only 1 and 13 are factors. So I hope the definition of prime numbers is clear. Now we can see when two numbers are called relatively prime. A pair of numbers AB is called relatively prime if their GCD is 1. The greatest common divisor is 1. We can see examples. If you look at 8 and 15, try to find the factors of 8 and then factors of 15. You can verify offline that these are the set of factors. Now you can easily observe that their common factor is only 1. Another example, pair of relatively primes. You come up with the factors of 12 and then 25. Verify that the factor set is correct for each number, and now assuming that these are the factor sets, then their common divisor is 1, only 1. And now another pair, you come up with the factors, look at the intersection, you will get only 1, and so GCD must be 1. Another pair of relatively prime numbers, come up with the factors, look at the common factors, only 1. Now I hope you got the definition. Two integers are said to be relatively prime if and only if their GCD is 1, and GCD is the greatest common divisor or common factor. Now it is not difficult to prove that a pair of numbers AB is relatively prime if one of them is prime and the other one and they are not the same numbers. And if you take a prime number, say like 17, it does not matter whatever be the other number, they must be relatively prime because a prime is having only that number and 1 as its factors. And if this number is different than the other number, then the only common factor can be 1, and so it is an easy statement to prove. Now we can have a theorem which tells us that for any integers a, b and p, We are taking 3 integers and we are not taking that P as prime. These are just 3 integers. And suppose you know that P and A are relatively prime and P and B are relatively prime. So P is the common number there. P is relatively prime to both A and B. Then the theorem claims that P is relatively prime to the product of A and B. Whenever P is relatively prime to both A and B, P must be relatively prime to the product of A and B. We can prove it. Suppose P and A are relatively prime. So GCD of P and A is 1. Then from a theorem that we proved in a previous lecture, we know that the GCD of any two numbers is the smallest possible positive linear combination of A and B. So it is of the form Px plus Ay, and we need the smallest possible value of that as the GCD, and here GCD is given as 1. So the smallest positive linear combination must be 1, and this is what we know from that theorem. If you are not able to recall that theorem, go back to that lecture. I think it is 22 or 23, and then recall it. Similarly, if we assume that P is relatively prime to B, then we can see from that theorem that linear combination, the smallest positive linear combination of P and B, that is Px prime plus Ay prime. Sorry, there is a typing mistake. This should be B. I will correct it. B prime, Y prime must be 1. And this is just an application of the theorem that we proved. If you are not able to recall it, please go back. And now you look at by taking these two, and you try to find the product of these two quantities. So we can say that this multiplied by this, the typing mistake is corrected here. You can see this is B, okay, and then the RHS must also be multiplied 1 into 1. LHS multiplied by this LHS is this. Now you just compute it. You multiply these two with Px and just remove the bracket. If you just multiply inside, you will get this equation. For the interest of time, I am not going to verify it now. You can do it offline. So take it as granted. This is exactly the equivalent formula. If you multiply inside, you will get this. And from this, I am going to take all the term where P is present, and I am going to take P as a common factor. P into, from this you will get xpx, right? 1p is taken out, xpx prime. From here you will get xby prime, and from here you will get what, ayx prime, right? Plus the only other term is this, that you multiply at ab into yy prime. You can write also like that because multiplication is commutative. Now you can observe that this is a linear combination of P and AB, right? P multiplied by an integer, whatever be that integer, it of course it is using P, that's okay, but it's P multiplied by an integer plus AB multiplied by an integer. So we are proving that a linear combination of P and AB is 1, right? And from a previous theorem we know that GCD is the smallest positive linear combination of two numbers. So it tells us that 1 is the GCD of P and AB because 1 is the smallest positive linear combination. There is no other smallest positive linear combination. Just after 0 you have only 1. Okay, so you are proving that the GCD of P and AB is 1, and hence you prove that they are relatively prime. And I hope you followed it. For the interest of time, I am proceeding to the next. And if you are not able to fully understand, please watch it again. Now the next theorem which tells us that for any two integers a, b and a prime number p, if the prime divides the product of a and b, then either p divides a or p divides b or p divides both a and b. We are going to prove it by applying the method of contradiction. Now for the purpose of contradiction, assume that say p divides ab, but these two are not correct. That is, it's not true that p divides a and it is not true that p divides b. So p is not dividing any of the numbers a and b. This is what we are assuming for getting a contradiction. And if p is not dividing a, then they must be relatively prime, because if p divides a, then the GCD must be p. And if they are if p, because p is a prime number, we have seen that a prime number and any other number, when they are not equal, the GCD must be 1. Similarly, we will get when you assume that p is not dividing b and p is prime, p and b must be relatively prime. We are almost done. Now from the previous theorem we know that whenever we have p is relatively prime to both a and b, p must be relatively prime to the product ab. Then it contradicts the fact that p divides ab. If p divides ab, the common factor must the GCD must be p, not 1. So this is a contradiction, because we are getting the GCD as 1. If they are relatively prime, they cannot have this condition where p is dividing ab. That means the common factor is p, not 1. But here we are getting the greatest common factor as 1. That is a contradiction. I hope it is clear. Now let us proceed. Now we are going to see a famous theorem from number theory, namely the unique factorization theorem, which basically tells that any composite number can be represented as a product of powers of primes. It's a complex statement, we can see with an example. See, 180 is not a prime number, it is a composite number. So whenever it is a composite number, you can represent it as a product. For example, this can be represented as 90 multiplied by 2. But 2 is a prime, but 90 is not. Now the same thing applies here as well. You can write 95 like this. These two are primes. You can apply the same thing for 45. Maybe you will get it as 15 into 3. It doesn't matter whether you take it as 15 into 3 or 5 into 9. It doesn't matter. I am just taking one. Now you have got 3 prime numbers and a composite number. Apply it on 15. Now you are getting all primes. So it is a product of primes, and it can be written as 2 raised to 2, because 2 2's are there, 3 raised to 2 and 5. So it is what I wanted to tell. Any number can be represented as a product of prime powers. This is a prime number, power 2, prime number, power 2, prime number, power 1. So any composite number can be represented as a product of prime powers, is what the unique factorization theorem tells us. And the theorem is going like this. There is a unique way to write a composite number A like this as a product of powers of primes. So A can be written as P1, which is a prime, to the power E1 multiplied by P2 to the power E2, etc., Pk to the power Ek, where Pi are prime, and we can always arrange it in the increasing order of prime values. So this is unique factorization theorem. It is very intuitive as shown by this particular example, and I am leaving the proof as a homework exercise. Another example you can see, if you look at the composite number 6000, you can see that you can write it as a product of prime powers, 2 to the power 4 multiplied by 3 multiplied by 5 to the power 3. Just verify that it is correct. So now let me proceed to modular number systems. I hope you have studied about modular number system in your bachelor course in engineering. Let us recollect what are modular number systems. So its modulo n numbers represented as on the set of integers, it is represented as integers modulo n. This is the notation, and it is nothing but this set from 0 to n minus 1. There is no other number in that set. So if you look at Z100, it is from 0 to 99, and that's it. And if you take three integers a, b and n is that modulo, okay? And if you know that a mod n and b mod n are same, that is, when you divide both a and b with n, you will get the same remainder. You are looking at two integers, when you divide them with n, you are getting the same remainder. And then we can say that a is congruent to b modulo n. That is how you can read it. A is congruent to b mod n. When you can say like that, when you divide a and b with n, you will get the same remainder. Then you are saying that a is congruent to b mod n. Or in this number system, they are equivalent is what it is saying. They are not equivalent in the set of all integers, but in this modular system they are equivalent. They are the same. Example, you take a as 3, b as 10 and n as 7. You first try to find what is a mod 7, n is 7, right? A mod 7 is what we are going to compute. Substitute a as 3, it is 3 mod 7, which you know that it is 3. Remainder of dividing 3 by 7 is 3. Now you see what is b mod n. Substitute b as 10 and n as 7. So it is nothing but 10 mod 7 is 3, because 10 divided with 7 will give you 3 as a remainder. So now you are getting 3 and 10 having the same remainder when divided with 7, and from this definition now you can say that 3 is congruent to 10 mod 7. I think with this example, this congruence relation is clear. It basically tells you that they are equivalent in the set of all integers and they are the same on the modulo system. For an integer a in the modulo n number system, in this number system, we are going to define a class represented as square a subscript n. And what is it? It is nothing but the set of all integers such that a is congruent to b modulo n. That's it. It is a notation representing the set of all integers b such that a and b will have the same remainder when you divide them with n. Okay, that is a is congruent to b modulo n. You collect all such b, that is this set. You can look at an example. When n is equal to 3, which are those classes? This is the first one. Class represented by 0, it is an equivalence class, and that is why basically it is represented like this, and this is an equivalence relation you can prove. And this is the class of all integers. When you divide that integer with 3, you will get 0 as remainder. That is true for all numbers in this set. Similarly, you will get a disjoint set when you divide them with 3, for each of them when divided with 3 will give you 1 as the remainder, and then the only other class, equivalence class, is for remainder 2. I hope you are getting me. So when n is equal to 3 in this number system, you will have only 0, 1 and 2 as numbers, and all these numbers will be represented by 0 in the modular system, and all these numbers will be represented by 1 in this modular system where n is equal to 3. And similarly, all those numbers, when you divide them with the n, if you get 2 as the remainder, then 2 will be representing all those numbers in the modular system. So note that in a modular system, a number may be representing infinitely many integers. I hope you are with me. Now let us proceed and see what is this algebraic object which is called a group. A group is a pair S and an operation, where S is a set and this is an operation, binary operation on S. It could be any binary operation satisfying a number of properties. The first property is that for all pair of numbers in S, if you apply this operation between them, then the result will be in S itself. For example, if you look at S as the set of natural numbers and this as the addition on the set of natural numbers, or even multiplication, you can see that it is closed. So the resulting element when you operate on any two numbers on the set will be in that set itself. An example which is not a group is natural number with subtraction. If you subtract 10 from 2, the result is minus 8, which is not a natural number. So that's not a group, that cannot be a group. A group must satisfy the closure property on that operation. And then next property is there is an identity element in the set S. If you take any element of S and if you apply the operation with E, you will get the same element back. That is, A operated with E is nothing but A, which is same as E operated with A. It doesn't matter in whatever order in which you do it. It is either A operated with E or E operated with A. The result must be A. So this is what is called the identity of the group. So every group must admit an identity element having this property. The third property is associativity. That is, if you operate like this, first you operate A and B, then the result is operated with C. It is same as first you operating B and C, then you operate that with A. Or first you operate A, you find A, then after you find the result of B operating with C, and then you apply A with that result. So these two must be same. It is called the associativity. And now the fourth property is inverse. That is, for all element A, there must be an inverse. What is the inverse? If you apply that operation with the inverse on A, you will get the identity element as result. That is, there exists a unique inverse B for every A such that when you operate A and B, you will get the identity element. And it doesn't matter in what order you perform that operation. Either A operated with B or B operated with A, you will get back the identity element as the result. Okay. So this is inverse. So this is a group. A group is a pair, a set and an operation where the operation is closed, meaning if you apply that binary operation on any two element on S, the result must also be in the element. There must be an identity element, meaning if you operate A with that identity element, you will get A as the result back. It's not going to change. Associativity is this, I think you are getting me, and inverse. Inverse means for every element there is a unique inverse B, such that when you operate A and B, you will get the identity as the result. Doesn't matter whether you operate A with B or B with E. And not that the commutativity is not there. So this is a group. Example is set of all integers with addition. This also I am leaving as an exercise. You verify that it's closed. I mean, the sum of any two integers is an integer. If you look at the identity, it is 0. Any integer A plus 0 is A itself. So 0 is the identity. Associativity says that A plus B plus C is nothing but A plus B plus C. That also you can easily prove. And now it is there is an inverse also. What is inverse? For every A, the inverse is minus A. A plus minus A is 0. And in addition to this, maybe this group is satisfying some extra properties like commutativity. That doesn't matter. Now we are going to modular addition. You consider this group, and what is this set? The modulo 6 numbers, where addition is what you are going to look at. These are the modulo 6 numbers. These are the numbers, and if you look at their addition, that can be completely represented by a matrix like this. For example, if you look at the addition between 3 and 4, what is 3 plus 4? It is 7. But 7 is not a number in this set. So you are looking at the representative element of 7 in this set. What is 7? 7 is congruent to 1 modulo 6. Because when you divide 7 with 6, you will get 1 as the remainder. So the answer is 1, because 1 is the representative element, or it says that in the modulo system 7 is represented by 1. Another example, what is 5 plus 5? It is 10. What is 10? 10 is congruent to 4, because when you divide 10 with 6, you will get 4 as the remainder. So the result is 4. And verify that for every other pair, there are 36 pairs, the value computed or shown over here is correct. So I am leaving that verification as a homework exercise. Now we are going to the last part of this lecture, where you can see a new set which is Zn star. Zn you know, right? The modular number system from 0 to n minus 1. But Zn star is those numbers in Zn such that that number is relatively prime to n. That is GCD of A and n is one example. If you look at Z15, you know that you have 0 to 14, right? And from that set, if you take only those elements which are relatively prime to 15, you are getting this set, right? You verify that these are relatively prime to 15, and in Z15 there is no other number relatively prime to 15. I am leaving that again as an exercise for the interest of time, and moving on to an operation which is called modular multiplication. And now you consider this group. What is this set? It is the subset of numbers in Z15 which are relatively prime to 15, and you look at the multiplication operation on that. And here we found that these are the elements in this set. So these are the only elements, and you consider multiplying any two elements in that set. For example, if you look at 11 multiplied by 8 in this system, the value is 13. We can verify it because 11 multiplied by 8 is 88, which can be written as 15 into 5, 75 plus 13. So when you divide this number with 15, you will get 13 as the remainder, and 13 is a number in this system. 13 is relatively prime to 15. So the result is 13. Okay. And here how many pairs are there? 64 pairs are there, right? And 64 values are computed and shown in this table. As a homework exercise, you pick some of the pairs uniformly at random and verify that the result is correct. And with this, we are finishing this lecture, and I am giving you 2 exercise problems for you to practice and understand what is modular addition and modular multiplication. You are just asked to show the modular addition table for this and the modular multiplication table for this. Today we have recollected some more basic elements from number theory. We discussed about prime numbers, relatively prime numbers, some theorems or results on primes and relatively primes. Then we have seen what a group is. A group is a pair, a set and an operation where that operation is closed. It admits an identity element, it is associative, and there exists an inverse. So such a pair is called a group, which is an algebraic object. Then we have seen modular number system, Zn star, and we also have looked at modular addition and modular multiplication. In the next lecture, we shall discuss about an algorithm for modular multiplication. Thank you.